this is the second part for part 4 for transition metals, because it's such a big syllabus point. So yeah, we're going to continue on that part 4 video. Okay, so we have looked, when we were finishing up, the manganese complexes, right? And we have seen the color changing as it goes through, first of all, deprotonation, and then oxidation, and then further oxidation accompanying hydration, right? So pink to brown, a pale brown to brown to very dark brown, okay? So that is our order of color changing and the oxidation states of manganese, okay? Now we're moving on to iron. So we first of all have Fe2 plus ions. In the Fe2 plus ion aqueous solution, it's a pale green solution, okay? And if we add some sodium hydroxide, it's going to react with the OH minus ion, deprotonation occurs, and we're gonna get this complex with no overall charge, and we're gonna get 2 water molecules because the OH minus accepted the protons. And now we're going to have our green precipitate, okay? So from pale green solution, we got a green precipitate, okay? So if we add ammonia solution, not ammonium, ammonia solution, then we will basically look at the same observation. It's just that the chemical equation looks very, very slightly different. So the green precipitate, when it forms, it's going to change into a brown precipitate. So we have this formula Fe, and then we have 3 water ligands and 3 hydroxide ligands on standing in air as it is oxidized. So the Fe over here, the oxidation state, is going to be 3 plus, not 2 plus anymore, because it has been oxidized, okay? This phenomenon is basically rusting, okay? So that's why rust is around, like red-brown in color. So if we start with Fe3 plus aqueous solutions, the solution is going to have a color yellow-brown color solution. And when deprotonation occurs upon adding sodium hydroxide, or similarly ammonia solution, we'll look at the equation again a little bit later, but basically deprotonation occurs and we're going to get a brown precipitate, Fe, with 3 water ligands and 3 hydroxide ligands, just like we saw over here. So it has been, the Fe2 plus becomes oxidized into this precipitate, right? So this is actually fully oxidized. So there will be no further reaction with excess ammonia or sodium hydroxide, and also because it is fully oxidized, there is not going to be any further changes in just standing in air, okay? So the next one is cobalt, okay? So cobalt, this guy's a little bit different, so you have to memorize a little bit more for cobalt. First of all, cobalt, when it is surrounded by water ligands, it is a pink solution, okay? So anhydrous cobalt is cobalt salt is basically a test for water. So if there is water present and if you basically drop water onto that salt, it becomes pink because this complex forms. So if you add a little bit of sodium hydroxide, the OH minus ions, deprotonation occurs and you will get a blue precipitate with 4 water ligands and 2 hydroxide ligands on cobalt, okay? And yeah, consequently we get 2 water molecules coming out. And actually there is no further change with excess sodium hydroxide, okay? But if you add excess ammonia solution, then you will see another color change. Now over here we're seeing ligand exchange because the ammonia ligands are replacing the water and hydroxide ligands, okay? So we get a 6 ammonia ligands surrounding the cobalt 2 plus ion as a central metal ion. And now this is going to be a pale yellow solution, okay? And then this will become a dark yellow solution upon oxidation. So cobalt changes its oxidation state from +2 to +3, okay, when it's standing in air. So we have 4 colors over here for cobalt. So first of all, pink and blue, and then if we are adding more ammonia solution, then we get a pale yellow solution, and then we get a dark yellow solution on standing in air, okay? Memorize those colors. And now we have nickel. So nickel is kind of similar to cobalt because it won't have further reactions with one of those reactants. So first of all, we have the sodium hydroxide. Again, same thing happens. I'm really tired of saying deprotonation because it keeps happening. But yeah, deprotonation occurs. The hydroxide ion reacting with the H plus in the water ligands, and yeah, this is formed. So this is the green solution. Nickel 2 plus aqueous is green, and when the precipitate forms, it's still green. Okay, a green precipitate. Chromium Cr3 plus is also green solution in the green precipitate, so be aware. And yeah, and if you basically use NH3, the equation looks very slightly different again, but we have the same complexes forming and what we're starting with, okay? And yeah, the observation's the same. With excess sodium hydroxide, there is no further observations, okay? However, if we have excess ammonia, then we get ligand exchange occurring again, and we get a deep blue precipitate, okay? Not precipitate. This shouldn't be precipitate. This should be a solution because we have ions. Okay, not solutions, but solution. Yeah, I'm sorry. Over here. Now we're gonna look at copper. Copper, aqueous ions, copper 2 plus aqueous ions, the solution is actually pale blue, okay? And if we add sodium hydroxide, deprotonation occurs, and we get a blue precipitate, okay? So pale blue solution, and then blue precipitate when we get this formula, okay? And if we use NH3, same thing happens, deprotonation, but we get ammonium ions. And with excess ammonia, not with excess sodium hydroxide, but with ammonia, we get a deep blue solution because over here, the ammonia actually is replacing 2 of the hydroxide ions and 2 of the water ligands, okay? So yeah, that is the formula of the new complex formed, and that complex has a color of a deep blue. So we get a deep blue solution, and you can see the replaced ligands over here as well. So that is with copper, okay? Now we're looking at zinc. This one is another amphitheatic species, okay? So we'll look at the amphitheatic behavior of zinc precipitates in a minute. But first, we have the sodium hydroxide. Again, deprotonation, same thing. We have NH3, NH4 plus, same thing, same complexes, deprotonation. So with excess sodium hydroxide, we will be getting, why do we have the wrong formula? Okay, sorry, this has to be 2, and this has to be 4, right? And yeah, so that this charge makes sense. I'm sorry if I apologize. Yeah, so we will have 4 hydroxide ligands, and we would have 2 water ligands because further deprotonation occurs, okay? So I have changed that. This has to be like changed for all the slides, but I'm sorry, it has to be 2 and 4. So yeah, this is further deprotonation. And because zinc, remember in part 1 we have discussed that scandium and zinc, they're not transition metals because they don't have ions that have a partially filled 3D orbital. That's why these are all colorless, and we have white precipitates, right? So they don't have colored complexes. So yeah, further deprotonation, and we get colorless solution, but the white precipitate is going to dissolve, okay? And with excess ammonia, we're going to get, actually there could be 2 results. Both results don't really appear differently in observations, but yeah. If we have 4 ammonia molecules reacting with the precipitate, then we will get ligand exchange and also accompanying change in coordination number, right? So we have over here 6 ligands. Why is the 2? Yeah, 6 ligands over here, and we would get zinc NH3, 4 ammonia ligands surrounding the zinc 2 plus ion. So the coordination number changes from 6 to 4. right? Yeah. So, and we get all the other ligands just coming out. And we could have 6 molecules of ammonia replacing all these ligands. So in this case, though, we wouldn't be accompanying coordination number changing, right? It's just ligand exchange, okay? But both can form, but this zinc surrounded by 4 ammonia molecule, this complex is more stable, okay? So just know that. And we're going to see the amphitheatic behavior of zinc as well. Just a second, I am sorry. Why is it not working? Okay. Yeah, the amphitheatic behavior of zinc precipitates. So when it reacts with acid, it's basically the same for zinc as well, just like chromium. The 2H plus is going to be accepted by the hydroxide ligands and form 6 water molecules. And if we have OH minus, the base being added, alkali being added, then it's going to react with the H plus over here. Deprotonation is going to happen. So we're going to form the zinc ion, zinc 2 plus ion being surrounded by 2 water ligands and OH 4 hydroxide ligands, and then we get the waste product as 2 water molecules, right? Yeah, because deprotonation occurred. So yeah, that is our, the white precipitate is going to dissolve into a colorless solution because now we're forming ions. So that is the amphitheatic behavior of zinc precipitates. And that is the end for 17.22, that syllabus point, the really long one. Yeah, and I will see you in the next video where I talk about catalysts, okay? This will be the last transition metals video. How many videos do we have? I think we have 6. Is it 5 or 6? We have 6. I didn't expect this to be this long, but oh well, I gotta cover everything, right? See you in the next video.